There we go. All right. So we talked about approximate lecture schedule. And what I'm hoping that I'll get from everyone by the end of the day is the Chapter 4, Part 1 homework and the Lab 3. So again, if you need some extra time, just let me know. And a lot of you have already emailed those in. And so here is my email right up here. You can also email them through Canvas. And then come Wednesday, I'm assuming we are going to be finishing up Chapter 4 and starting Chapter 5. It will be a different internet link, so I will be posting that soon. And of course, the lab is postponed. And my hope is that you'll have the Chapter 4 Part 2 homework due by Monday the 23rd, which is a week from today. So any questions on anything coming up? Okay, so all right, so one thing I wanted to talk about, and let's get to our homework. So I wanted to talk a little bit about your next homework assignment because there is one on here, and in fact it's number 1, and it tends to be a little tricky for students. So let's do a couple of these together. So these are working with our electrolytes, and we're trying to figure out what is in solution. So let me start off with something like NaOH. So NaOH is a base. Do y'all remember if it's strong or weak? Anyone remember if it's strong or weak? You can either yell out or you can, I hear Nicole saying strong. Yes, it is strong. So Nicole, how did you know it was strong? And I hear Juan saying strong as well. Either of you, how'd you know it was strong? Anyone remember how we can tell if something is a strong base? Okay, it does have OH, and it can dissociate completely because it was part of the list I gave you, exactly. So let's take a look at our PowerPoint slides, and I'm going to last time. Way back. All right, so here was our rule for bases that we looked at last time. We said our strong bases were our group 1A hydroxides or 2A hydroxides, calcium and below. So because sodium is right here, it is part of the 1A hydroxides, that's what makes it strong. So all the bases will have the OH, but only the strong ones would dissociate completely. So it is on the list that I gave you here. So I do want you to know your strong acids and strong bases. So any questions on how we would know that NaOH is strong? Oops. That's where we were. Okay, so let's talk about what I'm asking you to do on the homework. So first off, is it a strong, weak, or a non-electrolyte? So if NaOH is a strong base, let me grab. If it is a strong base, what kind of electrolyte is it? What do y'all think? Strong, weak, or non-electrolyte? Excellent. I'm seeing a lot of strongs in there. All right, so it is a strong electrolyte. And just for fun, let me make a list here. So strong electrolytes. There were 3 things that were strong electrolytes. We just said they were strong bases. What are the other 2 categories? I hear your strong acid and ionic compounds. Yes, so strong acid and ionic, and I'm going to say soluble, by which I mean aqueous ionic compounds. All right, so any questions on how we could say that NaOH is both a strong base and a strong electrolyte? Oops, sorry about that. All right, so next up we want the species in aqueous solution. So what we're looking at is what does it break up into? And what we know about NaOH, and let me do it right over here, is that NaOH breaks up completely into sodium plus hydroxide. All right, so if I'm looking for the species in aqueous solution, it is these right here. So species in aqueous solution, we're going to have sodium and hydroxide like so. All right, so any questions on why I would say that Na and Na plus and OH minus are the species in aqueous solution? All right, so those are the species that are actually floating around. NaOH as a whole does not float around because it breaks up 100%. All right, so next up it says list the major species in solution. Some things are going to have major and minor species, and those are going to be the weak electrolytes. But for us, with the strong, it's going to be sodium and hydroxide. Those will be our major ones. So I want to do a weak one and a non-electrolyte with you as well, but any questions so far? Any questions on how we did the NaOH? Okay, so next up, let's take this HNO2. So is that strong, weak, or a non-electrolyte? What are we thinking? Well, first off, do y'all agree that it's an acid? Okay, so I'm hearing that yes. Now, is it a strong acid or a weak acid? So give it a guess. You got 50-50 chance of getting it right. Strong or weak? All right, so I'm hearing some brave people say weak, and that is correct. All right, so you're going to know your weak acids in a similar way to your strong bases. We want to look at the list. All right, so way back here we looked at our strong acids versus our weak acids, and we said there were 6 strong acids, and if it is not on this list, it is weak. So the one we're just looking at, HNO2, would you all agree that it is not on the list of strong acids? Ah, excellent. Thank you. All right, so it looks a lot like it, but it's different. So this is HNO2 as opposed to HNO3. Because it's not on the list, we're going to call it a weak acid. Because there are 6 strong acids, this is not one of them, therefore it qualifies as weak. So any questions on why we can call HNO2 weak? All right. All right, so here is our HNO2. It's a weak acid. What kind of an electrolyte is it? Strong, weak, or a non-electrolyte? All right, so I'm hearing both non and weak electrolytes. It turns out it is a weak electrolyte because it is a weak acid. So our weak acids and bases are going to become weak electrolytes. Any questions on that, on why it's a weak electrolyte, not a non-electrolyte? So let's just go over our weak electrolytes. I'm going to add a page in here. All right, so our weak electrolytes these are going to be weak acids and weak bases. All right, so if we have something like HNO2, What we said is that it does break up, but it also gets back together. So it's considered a weak electrolyte and a weak acid because it breaks up and it gets back together. All of these live in solution at the same time. But if for a weak electrolyte, this is the major species. These right here are the minor species. And I know for biology majors, that word species means a whole different thing to you. In chemistry, we just mean it as some type of chemical. So the major species will be the entire acid put together because very little of it breaks up at any given time. The minor species are going to be the ions because we get only a little bit of those ions. So questions on anything so far here? Okay, so let's go back over, and we are trying to first list all of the species in aqueous solution. So everything that's in there, the HNO2, H plus, and NO2 minus like so. All right, so for HNO2, the entire molecule is here in the aqueous solution, and that's going to be true of any weak acid or weak base. You're going to have the molecule as well as the ions. But when we go to the major species, if it is weak, the major species is the molecule. We only get a few of those ions. So any questions about how we did NaOH or HNO2? All right. So next up, let's try the water up here. So what is water? A strong, weak, or non-electrolyte? All right, so I'm seeing lots of non, and that is correct. So water is a molecule, so it's going to stick together. All right, so what is swimming around in solution for water? What is the list of all the species in solution? What are we going to put for that? Correct, just H2O, because that's all it is. It's not going to break up. Therefore, the major species is also H2O. So that's what we're going to see for all non-electrolytes. Okay. So I've done a few of these on the homework. Any questions on anything that I've done here? Okay. So what I'm going to do is copy this over to our notes so that you have these. So let's see. Actually, I take that back. Instead of putting them right in the middle here, I think I will create a separate note for these, and I'll call these the homework chapter 4 part 2 notes. All right. That way they don't get confusing later on. Okay. All right, but questions on anything that we've done so far? So I just want to put this screen up again because I know we have a few people who joined us a little late. So this is kind of our schedule. We're going to lecture for about an hour, then we'll take a 10-minute break, another hour, and then the rest of class is just office hours, and the labs and exams are postponed right now. All right, so the very last time we were together, when we actually got to see each other face to face, we were doing net ionic equations. So we first wrote a balanced molecular equation, and then today we're going to work on checking to see if that reaction happens or not. We are going to dissociate all strong electrolytes, cross out anything that remains unchanged from the left to the right side, and then we'll write the net ionic with everything that's left over. So last time we were together, this is what we did. We did our molecular equation, and that one was given. So the molecular equation is the equation you're used to seeing. The total ionic is when we broke up all strong electrolytes, and only strong electrolytes got broken up. So that means strong acids, strong bases, and aqueous ionic compounds. Then we crossed out our spectators, things we see on the left and again on the right. I labeled those spectator ions. And then here was the net ionic, what was left over. Okay, so questions on anything we did for that very last example last time? And I realize my U here looks a little funky, so I'm going to rewrite that. Okay, so I hear Juan asking, strong electrolytes get broken up. Yes, so only the strong ones get broken up. We will not break up our weak ones, so we can't break up a weak acid or a weak base, and we also can't break up solids, liquids, or gases. All right, so other questions so far? All right, so one of the rules, let's get down to here, that we didn't talk about yet was number 2. Check to see if the reaction occurs or not. So I want to do that now. And normally that's something we do in our very first step because you don't want to have to go through the whole problem and then at the end you're like, oh, I didn't even have to do this. So what we're going to do is we're going to look at our products right over here and we want to see if this reaction happens or not. So what we're going to look at is this list right here. So we said that one of these 5 must be produced. So 3 of them were our states, solid, liquid, or gas. And then we have weak acid and weak base. One of those must be produced. So what did we produce here that allowed us to have this chemical reaction? Excellent. So I'm seeing the solids and the PbI2. That is correct. So this solid right here, we produced this. And we say the production of that solid drives the reaction. It pushes that reaction to happen, and it is because we produced this solid that, first of all, the reaction happened, and second of all, we can give it a special name, and it's a name we talked about last class. Anyone remember the name of this reaction because we produced a solid? There it is, precipitate, yes. So it is a double replacement because they switch partners, but it is a precipitation because we produced a solid. So I'm going to say precipitation reaction. So just to go back for a moment, and you guys will have to tell me if I'm scrolling too fast and you need the screen for a little longer. But just to go back, way back when, here we go. So the precipitation reaction is a special type of a double replacement, and it's a double replacement where a solid is produced. So any questions about how we knew it was a precipitation reaction? Or how we knew that this reaction would occur? Okay. All right, so we also took a brief look at the solubility table, but we didn't go into depth, and I want to go through that with you because in the following reactions, we're going to have to determine what the state is, aqueous or solid. Let me go ahead and take this little guy out of our way. All right, so let's imagine that we did not know what these states were. I want to show you how to find these states. All right, so I'm going to start off with the Ki right here. And what I told you is on tests and quizzes, I will give you this solubility table, but I want you to know how to use it. So here we're going to look for either the K or the I. They will always agree with each other. So here is the potassium, and it says it's always soluble. And what we said about soluble is soluble means it will dissolve. Now, in case you were thinking, well, I don't want to look at the K for some reason, I have some issues with K, I want to look at the iodide. It is right over here. And it says it is soluble with any ion except silver, mercury 1, or lead. Well, we don't have silver, mercury 1, or lead, so this tells us that I- is soluble. So any questions on why Ki will be soluble, or in other words, aqueous? Okay, so let's go ahead and mark this one as aqueous. Next up, we have lead nitrate. All right, so for some of these, you won't find both the cation and the anion, but you will always find at least one of them. So in this case, we have the nitrate, and it says nitrates are always soluble. That means anything with a nitrate, no matter what its cation is, it will always dissolve, it'll always be aqueous. So I'm going to say that this one is aqueous because it contains a nitrate. So any questions on how I labeled or why I labeled lead nitrate aqueous? All right, so given what we just said about the nitrates, what about KNO3? Do you think this is aqueous or solid? Excellent. So lots of great answers. Excellent. All right, it is indeed aqueous, like so. All right, so any questions on how we determined that KNO3 was aqueous? All right. So next up we have the lead iodide, PbI2. So I'm going to go to the table. And again, lead isn't listed separately, so in this case we have to use iodide. And here it says that it is normally soluble, but it becomes insoluble if it has one of these three that are listed. And let me zoom in for us. All right, silver, mercury 1, or lead. And there's the lead that we've got. Since we have lead, iodide is now insoluble, which means a solid. So that's how we would know that PbI2 is indeed a solid. So any questions on how we came up with any of those states? Excellent. All right, so again, on a test or quiz, you're going to get the table. And by the table, I just mean the table itself. Let me go ahead and draw an outline here. This part right here. You need to know the meaning of soluble and insoluble, but you're going to get that table. But I do need you to know how to use it, just like we did just a moment ago. All right. Questions on anything that we did labeling our states? If it was PB3 plus, would that change? You're right, it actually would change. We don't really have a lead 3 plus, but we do have a lead 4 plus. So if we had PBI4, you're correct. That one would then be soluble. Good call, Juan. I don't plan to trick you guys like that on a test or quiz, but in general, Juan is correct. If you had lead 4, which would be PBI4, it would not fall in the exception category. It would be soluble. All right, other questions so far? Excellent. Okay. And again, if you'd prefer to just ask your question, you're always welcome to unmute and just kind of yell it out. All right. So let's go ahead and do the first one together because I know it's been a while since we did our last net ionic equation, and then I'll have you do the next one on your own. So first off, potassium hydroxide. So what's the formula for potassium hydroxide? All right, so I'm hearing a KOH. Do y'all agree on KOH for potassium hydroxide? Looks like I got a few of you there. All right, excellent. All right, next up, we have sulfuric acid. So how do we write sulfuric acid? Oh, and I see it coming up already. Excellent. So I see an H2 and I see an SO3. What do you guys think? H2, SO3 like so? SO4, thank you. Excellent. Any questions on how we came up with our chemical formulas? No worries, it's hard to type fast. All right, so these were already told are aqueous, so I'll go ahead and write aqueous here. Next up, we got to come up with our products. So we're going to do our double replacement, also known as double displacement. So I'm going to write out my K plus, OH minus, H plus, and SO4 2 minus. I want you all to take a moment on your paper and write out the products, then we'll talk about them together. But go ahead and come up with your products. As you're working, if you have any questions, feel free to do the chat box. You can chat and select everyone. You can select me specifically, or you can select anyone in the class. All right, how are we doing? Would anybody like more time on these? And I hear on the text, let's see, H3O, and H3O is not a possibility. But I see some really good things in here. Does anybody want some more time before we do it together? Okay. All right, so what we're doing here is we are combining our outer ions and we're combining our inner ions, and the inner ions we're going to switch around. And I see a couple of you with some really good answers here. So when we combine the potassium and the sulfate, so what did you get with K and SO4? A few of you said it to me privately, but there we go. K2, SO4 like so. Any questions on that K2, SO4? All right. So now our next one is what? What's our other product? Excellent, water. All right, so I saw on the chat a couple of you asked about H3O because you were trying to combine these two right here, but remember we are actually combining, the ones down at the bottom. So this is why I write them out at the bottom, because you've got to combine them in their original form. So originally it's an H plus, not an H2. So that's why it becomes HOH or water. So any questions on why it is not H3O like so? All right, go ahead and take a moment to balance this, and then we will go through it together. Oops. All right, how are we doing? Does anybody want some more time for balancing? All right, so it looks like we got a couple of you who are bravely volunteering. You're balancing, so I hope you don't mind. I'm going to go ahead and write your coefficients in and see if everyone agrees. So it looks like a 2 in front of the KOH and a 2 in front of the water. What do you all think about this balancing? All right, so I'm seeing some yeses. Excellent. All right, any questions? Let's see. If we had a weak acid, would we have a double arrow? That's a good question. So technically, yes, we don't require you to do it in this class, but you're right. Technically, if you had a weak acid, you're correct. It would look like this, and we teach you how to do that in Chem 1B. So for this semester, you don't have to, but you are welcome to, and it would be more correct. All right. So any questions on the balancing or anything else that we've done so far? All right. So what we've just done can be called a molecular equation, like so. All right, the next thing we need is our total ionic equation. So for the total ionic equation, we're going to break up all of our strong electrolytes. So KOH, what do we think? Is that a strong electrolyte, a weak electrolyte, or a non-electrolyte? Excellent. So I'm seeing some strongs, and that is correct. It is strong because it's one of our strong bases. So really quick, I'm going to flip back. There we go. So it is a strong electrolyte because it's a strong base. It is this right here, this potassium with a hydroxide. So any questions why KOH would be considered a strong electrolyte? Okay. Okay, so we break up our strong electrolytes. So I'm going to say 2K plus aqueous like so, plus 2OH minus aqueous like so. Because we have a 2 out in front, it does apply to both the potassium and to the hydroxide like so. Any questions on what I've done so far with breaking up our KOH? All right, so next up, We need to look at our H2SO4. What do we think? Strong electrolyte, weak electrolyte, or non-electrolyte? Anyone want to give it a shot? All right, excellent. So I'm here seeing some strongs out there, and that is correct. So it is a strong acid, therefore it's a strong electrolyte. So when we break up H2SO4, we're going to have two H pluses plus SO4, 2 minus, like so. Now in this case, the 2 was below, it's a subscript, and I think AJ was asking about this last class. When the 2 is below, it applies only to the element right in front, whereas when it's out in front, it applies to both the K and the OH. So any questions on why we said there's 2 Ks and 2 OHs, but when we split up the sulfuric acid, we said there's 2 hydrogen, but only 1 sulfate? Okay, so questions on anything else that we've done so far? Okay. So I'm going to go ahead and draw my arrow here to the next line. And so now we've got to deal with our K2SO4. Would you all agree it's an ionic compound? Would anybody agree it's an ionic compound? Excellent. So it has a metal and a polyatomic ion. So metal and a nonmetal, so it qualifies as ionic. So we need to know if it's a solid or not, because if it's a solid, we can't break it up. We can only break it up if it's aqueous. So that means we have to go to our chart. All right, so looking at our chart, what do you guys think? Is this going to be solid or aqueous? Excellent. So I see a lot of aqueuses and solubles. Wonderful. All right, there's 2 ways to know this. First, here's potassium, and potassium is always soluble. Next up, we could have looked at sulfate, and sulfate is soluble unless it has one of those listed ions there. And by the way, you do not have to check both. Let's see, Michael, you are correct. Aqueous and soluble are interchangeable. And you do not have to check both the potassium or the sulfate. You have your option of doing either one. I was just showing you how to do both of them so you knew, but only one of them's needed. And yes, aqueous and soluble are interchangeable. All right. So this one is aqueous. Because it is an aqueous ionic compound, we are going to say it's a strong electrolyte, and we're going to break it up. So I'm going to say that there is 2 potassiums, aqueous, plus SO4, 2 minus, aqueous like so. All right, so any questions on how I broke up the potassium sulfate? All right, then we've got to deal with our water. So tell me about water. Do you think this one is solid, liquid, or gas? If you had to guess. Just at room temperature. If you have H2O at room temperature, is it frozen, is it gas, or is it liquid? Excellent, it is liquid. So water is a liquid, and that funky little fish-like thing is my L. So this is a liquid. Technically, aqueous means dissolved in water. If you have pure water, you need to label that liquid. And there's a really good reason we want to label that a liquid. Because we need a reason for this reaction to happen. We have to create one of these things: a solid, a liquid, a gas, weak acid, or weak base. We've just created a liquid, which includes water. So if you were to label it aqueous by accident, then it looks like the reaction didn't happen. So we want to make sure we label water as a liquid, because that is what will push this reaction to happen. Water is extremely favorable to form. So if we can form water, this reaction will definitely happen. All right, so I am going to write H2O as a liquid. I'm not breaking it up because it is a non-electrolyte. So any questions on how we took our molecular equation and we broke it up to the total ionic equation? And any questions on why I didn't break up that water? Okay. All right, so here is our total ionic equation, and I wrote it on 2 lines, but just for the heck of it, oops. I'm going to put it together on 1 line. It's going to squeeze down, so if you're looking at this on a phone, this is going to make it a little hard to see, but it really is just what's above. Just wanted to show it to you on 1 line. There we go. The reason I wanted to do that, let's grab this. All right, is because I want to start crossing out things we see on the left and again on the right. That is to say they're both a product and a reactant. Is there anything we can cross out? All right, so I see K. Yes, K can be crossed out like so. And I'm hearing SO4. SO4 we can cross out. All right, is there anything else we can cross out? And I hear no, and that is correct. There's nothing else we can cross out. So what we're going to do now is our net ionic equation. We're going to bring down everything we haven't crossed out. So I'm going to scroll off the screen just for a moment so we can title this. This is our net ionic equation. All right, so our net ionic equation is everything we have not crossed out. So it looks like we have some hydrogen, we have some hydroxide, and we have some water. It's my habit, and you don't have to do this, but it's my habit to write the cations first. So I'm going to say H plus OH minus goes on to form, oops, and I think I am missing, I dropped my 2. There should have been a 2 here and a 2 right here. Goes on to form H2O like so. And when I brought everything down, something I did is I dropped the 2's from everything. So we want to write this in the lowest ratio possible. So if you can write it as all 1-to-1, that's better than 2-to-2. So I've written hydrogen plus hydroxide come together to form water. If you prefer to say hydroxide plus hydrogen, you can do that. But you do have to reduce everything so that it's in its lowest ratio possible. So in other words, if you had 2, 2, and 2, I would ask you to erase those so it is 1, 1, and 1. All right, any questions on how we came, let's see. Oh, you're right, I'm so sorry. I just told you all about that and then I accidentally made the mistake I just told you not to make. Thank you very much for catching that. Good job, Andrew. All right, so any questions on how we came up with our net ionic equation? All right, so last class we talked a little bit about spectators. Do you guys see any spectator ions here? So I see a question, does a positive ion have to be first in the equation? And it does not, so you are welcome. To do this. That's perfectly fine. It's just a habit of mine to do positive before negative, but if you want to do the other way, perfectly fine. All right, so what about spectator ions? Do y'all see any spectator ions? Yes, the potassium and the sulfate. So if you have crossed it out, it is a spectator ion. And I'm going to put potassium and sulfate here. Here we're just identifying the ion, so you don't need to put 2. It's not wrong to say 2 potassium, but you don't need it. So you can just say potassium. All right, so any questions on anything that we've done here so far? How are the net ionic equations feeling? Good, bad, terrible? It's giving you nightmares? Good? Okay, excellent. So normally, if we were in our normal semester where I was seeing all of you in class, I would tell you a week from today we would have a quiz, but obviously it's not going to happen right now. But there is a practice quiz on net ionic equations. And since it looks like we may not get to have our quiz on net ionic equations, whenever it is we get back in class together and we do take our exam too, I'm going to promise you there will be net ionic equations. So please make sure you study your net ionic equations. All right, but questions on anything so far? Okay, so let's go ahead and take our break. It looks like it is about 5:50 on my computer, so oops, let's plan to be back about 6 o'clock. And I didn't take roll, and I'm not going to be taking roll on the computer, so if you came in late, you don't have to worry about that. But I will see you guys in about 10 minutes at 6 o'clock. But if you have questions for me, feel free to message me. You don't have to use the everyone. You can use the drop down menu to message me privately, and I will message you back privately. Aw. So Andrew, go ahead and mute yourself unless you wanted to talk to the class. You can unmute when you want to talk to people, but otherwise go ahead and mute. Thank you. Oh, they didn't have to disappear. There you go. 7, 8. So good. Let's see. We'll break down reactors. Hi, Erica. Welcome. All right, so let's go ahead and get started again. Just realized I happen to be drinking from my hydrogen mug. They do sell hydrogen mugs. All right. All right, so any questions about what we did before break to come up with a net ionic equation? All right. All right, so let's go ahead and try this one, and we'll do this one together as well. So I'm going to break everything down to potassium, and iodide, sodium, and chloride. So what I want you to do is come up with the products and also find the state of the products. So if you're on a computer where you can get that solubility table, let me switch our share for a moment. All right, so if you're on a laptop or a computer where you can get that solubility table is by going to, let's see, our handouts. Oops, let's go home first. And let's see, where are our handouts? There they are. And then you're looking at the solubility rules right here. Okay, so I'm going to go ahead and switch back. So go ahead and write down the beginning part of that equation, and then I will switch to the solubility rules here on my tablet. But if you prefer on your own computer, you can download them from the handout section of Canvas. How are we doing? Does anybody still need the slide that's up on the screen right now? All right, so it looks like most of you have this written down. Anyone still want this slide up? Okay, so let me switch back to that solubility table for you. All right, so you're coming up with the products and you're identifying their solubility. Let me see. I can put them on the screen. No, it's going to be too small for you. There we go. Again, if you get stuck, feel free to message me or message anyone else in the class. You can message everyone, a specific person, or me as a specific person. So several of you are figuring out the trick of this problem. All right. So how's everybody doing? Does anybody want some more time? All right. Okay. So let's head back over here. You combined your outer ions and your inner ions. So what are the two products that you got? All right. So I'm hearing a KCl and an NaI, yes. Excellent. So everybody get something similar to this, KCl and NaI? Or anybody get anything different? All right, so next question is this balanced? Excellent. All right, so now let's do our states. I'm going to look at the KCl first. And I'm going to go ahead and look at the potassium. I don't really need the chloride. It'll tell me the same thing. And it says anything with potassium is always soluble. So I'm going to go ahead and write an AQ here. So I'm going to shrink that a little bit. Any questions on why I said that the KCl is aqueous? All right, so next up I'm going to go to, let's see, the sodium iodide, NaI. And again, I don't need to check both of them. I can check just one. Oops. And I'm choosing to check the sodium. And it says sodium is always soluble. So that is aqueous. So any questions on how we found that they were both aqueous? All right. So next up, we're going to take a look at our conditions for a reaction occurring. And our conditions were we need a solid, a liquid, a gas, or a weak acid, weak base. Did we meet those conditions? Did we get one of those 5 things? Correct. Excellent. So you are correct. So in this case, we have no reaction. All right, so as soon as you see that we have no reaction, you're going to put an X through the arrow, and you can write no reaction or NR, which always feels weird to me because those are my initials, but you're writing somewhere that there's no reaction. So you can X through that arrow and put NR, or somewhere you can write no reaction. So any questions on this one on why there's no reaction here? All right, so let's just say you didn't realize that there was no reaction. Let me show you how it would work out. Oops. I'm going to erase that for just a second. All right, let's say we didn't realize that this was a no reaction. We said this is our total, this is our molecular equation. And then we moved on to our total ionic. And in the total ionic, so I see a good question from Angie that says if there's no reaction, you can't write a net ionic equation. That is correct, and I'm going to actually show you why that's true right now. So total ionic equation, we're going to break everything up. And when I say everything, I mean our strong electrolytes. All of these are soluble ionic compounds, so they all qualify. Okay, so I broke everything up because they're soluble ionic compounds, which makes them strong electrolytes. Now I'm going to go through and I am going to cross out everything I see on the left and again on the right. So there goes potassium, iodide, sodium, and chloride. Everything is a spectator. So in other words, there is no net ionic equation. And because we are mean, cruel people, sometimes on tests, when we ask you to write your net ionic equations, we might throw one like this in there, sort of because we're mean, cruel people, but also because we want to make sure you're checking to make sure this reaction actually occurs. So if you get 2 soluble ionic compounds for products, there is no reaction, and as soon as you identify that, you can say no reaction, but let's say you miss that and you keep on going, everything cancels out. So either way, you see that there's no net ionic equation. And let's see. So I see there's a question of, can we draw a double arrow for equilibrium? Let's see. So which equilibrium are you talking about? Is that, I just see the G there. Is that Jervin? Okay. Since they're both aqueous, you could, I suppose, but really they're the same. They're describing the same thing. So if I talk about this side of the equation right here, I'm saying those 4 ions are floating around in solution. And if you were to drive it or describe it on the right, you'd also say those 4 ions are in solution. So either way, they're all floating around. And you could talk about them with a double arrow if you want, but it would be more accurate to not have any arrow because there's no reaction. Does that sort of answer your question? You could do the double arrow if you wanted, but it'd be more accurate just to not have any arrow because there's really nothing going on. Truly equilibrium would be a reaction that happens back and forth, like liquid becoming solid, solid going back to becoming liquid, so there's actually something happening. Here, there's really nothing happening. Okay, excellent. All right, so other questions about this example here where there is no net ionic equation because everything is a spectator ion. All right. All right, so give this one a try. You're going to write the net ionic equation, and you'll need the states. So go ahead and write down the question, and then I will move back to the solubility chart. But you're going to do the net ionic equation for this. So you want to do 3 steps here. So you want the full molecular equation. Then you need your total ionic equation. You need your net ionic equation. And you'll also need to identify your spectator ions. And by the way, on a test, I would require that you show all of those steps. So go ahead and take a moment, write down the question, and then I will shuffle back to our solubility table. Again, if you have any questions, feel free to unmute and kind of yell it out, or you can message me privately, message everyone, or message that special someone in the class that you do lab with, or a new friend in the class. How are we doing? Does anybody need this screen anymore? Can I go ahead and scroll to the next screen? Okay, I'm going to go ahead and scroll. If you need that other screen back, you just let me know. And again, feel free to ask me questions, message me, or message somebody else in the class. All right, if you find an answer, go ahead and privately message me what you think the net ionic equation is. Also, if you have any questions, feel free to message me or message anyone else in the class. All right, so I see some people getting their net ionics together. So let's see. So I'm seeing some good net ionics coming across. And some good spectators. Excellent. All right, how are we doing? Would anybody like some more time to go over it? Some more time to work on it before we go over it, I should say? No? All right. So nobody wants any more time to work on it before we go over it? Okay. All right, so let's go ahead and give this a shot. We're going to start with our molecular equation. All right, so I'm going to start with one of the nice people who messaged me, and someone told me that they got HCl aqueous plus FeOH3, and they went on to H2O and FeCl3 like so. So first off, and let me leave off the states for right now, what do you all think of that for our molecular equation? It's not balanced yet, but what do y'all think? Anybody get anything different or anybody agree with it? All right, so I've got some agreement. Excellent. All right, so then let's say I am seeing a 3 here and a 3 over here. What do you all think of the balancing? Anyone want to agree or disagree with that balancing? Looks great. It looks good. Yes, excellent. All right. So now we were told HCl is aqueous. Now let's take a look at our iron hydroxide. So what we're told about our hydroxide right over here is that it is soluble with these right here, but it would be insoluble with any other ion. So we have FeOH3. What do you guys think? Is this going to be an aqueous or is this going to be solid? All right, so we're actually getting a good mix of solid and aqueous here. And so I see some solids and some insoluble. So if we are looking for iron hydroxide, would you all agree that there is no iron here? There's no iron in the top one? Okay, so these are the only ones that are soluble. Since iron is not there, we are looking right over here. So this is insoluble, so it becomes a solid. So any questions why we're going to call iron hydroxide solid? So those of you, I'm not going to scroll back and name who it was, but those of you who were thinking aqueous before, any questions on why now it's a solid? Okay, so sounds like we're all in agreement about that solid. Any questions on anything we've done so far? Okay, so we agreed that water is a liquid, and we know that that funky little fish is my version of an L. All right, so next up we go to our iron chloride. And here's our chloride, and it says it would be insoluble if it had silver, mercury, or lead, but it would be soluble with any other iron, any other ion. So here is FeCl3, so iron is our other ion. So here we're dealing with soluble, so this is going to be aqueous. So any questions why FeCl3 would be qualified as aqueous? Okay. So any questions on what we've done so far? All right. Now, does this reaction occur? Excellent. So I'm seeing lots of yeses. So why does it occur? Excellent, because water forms. Yes, because we have a liquid and that liquid is water. Yes, and some of you are saying liquid, so either liquid or water. That's the reason it happens. All right, next up, total ionic. All right, HCl is a strong acid, so I'm going to break that up and say 3H plus 3Cl minus. We do not break up our solids. We don't break up our liquids. And now I'm going to break up that iron chloride. So Fe3 plus 3Cl minus, like so. All right, so I know a lot of you were thinking that the net ionic was H plus OH minus goes to water, but any questions why I kept that FeOH3 together? Or any questions on anything else we've written so far? So I apologize if you hear a little background noise. It sounds like it's raining really hard, and what sounds like a chainsaw in the background is my cat snoring. She has quite a snore. All right. So now we're crossing out what we see on the left and again on the right, and it looks like we've got 3 chlorides on both sides, and it looks like that is all that we have that we can cross out. So my spectator ion that is Cl minus. Next up, I'm going to take 3H plus the FeOH3, 3H2O plus Fe3 plus AQ. All right, and this is the net ionic. Equation like so. There we go. All right, so any questions on how I did the net ionic equation? All right, so last time when we did a net ionic, I had you change it from 2 to 2 to 2 to 1 to 1 to 1. Basically, I had you reduce everything down to 1. Let me go back to that one. Way back here, I had you reduce everything to 1s all the way across instead of 2s. Now we can't do that this time because before I essentially divided everything out by 2, but I kept the same ratio. I can't do that here because we have 3's and 1's. If I had a different equation, let's say I had 3H plus 3Fe OH3 goes on to 3 waters plus 3 iron. I know this isn't balanced the way it is, but if I had this case, then I could cancel all of these out. But the equation we actually have, I cannot do that because we have a 3, a 1, a 3, and a 1. So does it make sense why I'm not going to reduce these all the way down to 1s? Or let me say, are there any questions on why I'm not going to reduce this? Why I'm not going to do something like what I have down here? Okay. All right, so let me go ahead and get rid of this. Any questions on anything that we've done so far with our net ionic equations? All right, so I want you to give this one a try. So you have aqueous solutions of sodium acetate and sulfuric acid that are mixed. So you're doing the same thing with these. You're going to do your molecular equation. Total ionic equation. Your net ionic equation. And you're going to find your spectator ions. All right, so I want you to give this a try and make sure you write down the problem, and then I will switch back to our solubility table. Sorry. Hi, Sarah. Welcome. So Sarah, we're doing net ionic equations similar to what we did last class. So go ahead and write down what's on the screen if you don't already have it, and then I'm going to switch to our solubility table. Anyone still need what's up on the screen here? Okay, I'm going to switch to that solubility table. All right, so when you get your net ionic equation, go ahead and message me privately. You're also always welcome to message each other privately and check your work. Oh yes, I'm sorry. I meant to show that to you and I totally forgot. Thank you for reminding me, Angie. Ah. All right, so I'm getting a lot of comments on no reaction. Remember, if you can form a weak acid or a weak base, that will drive the reaction. So it may be aqueous, but if it's a weak acid or a weak base, that will make that reaction happen. So double check your weak acids and weak bases. And remember, we're not going to break those up. For those of you who are still getting no reaction, go ahead and message me. All right, how are we doing? Would anybody like more time on this one? So I can't see you guys working, so you got to tell me if you want more time. Yes, please. Okay, excellent. Yes, go ahead and take as long as you need. Message me if you have questions. Also message me if you're getting no reaction for your net ionic equation. All right, so all right, so I'm seeing one net ionic equation up there. If any, oh, hold on. So I'm seeing one net ionic equation up there. Go ahead and post your net ionics if you're getting them. All right, excellent. And see a lot of good net ionic equations coming through. All right, seeing a lot of excellent net ionic equations coming through. So let's take a few more minutes on these. Okay, so all right, lots of great net ionic equations coming through. All right. How are we doing? Would anybody like some more time on this one? No? Going once, going twice? Anybody wanting some more time? Okay. So let's go ahead and give this a shot. All right, so we have our sodium acetate, which we're told is aqueous, plus our sulfuric acid, H2SO4, and this is going to react to form our sodium sulfate, plus our acetic acid, like so. All right, so any questions so far about how I wrote out that equation? So that is true, AJ. This does sound like snowboarding and skiing weather. All right. Any questions about how I wrote out that molecular equation? All right. So what did y'all get for sodium sulfate? Was that aqueous or solid? Excellent. So I'm seeing some aqueous coming through. All right, what about the acetic acid? Aqueous or solid? Excellent. All right, any questions on anything so far? Okay, so let's go ahead and balance this. So it looks like we're going to need a 2 in front of the sodium acetate, and that would leave us with a 2 in front of the acetic acid. So any questions on how I balance that, or anyone want to see me write out that balancing? All right. So that is our molecular equation. And I think a lot of the confusion that I was seeing was about these two aqueuses. So you have two aqueous compounds, and if they were both soluble ionic compounds, then it's true. They would both break up. We would have nothing to drive this reaction forward. But the tricky thing here is that this little guy is a weak acid. All right, so let's go back to our list. Way back here. So if we can form a weak acid, this reaction is going to happen. So since one of those aqueous compounds was a weak acid, this reaction is going to happen. Any questions on that? Any questions on why our reaction qualifies as chemicals that are going to react because we created that weak acid? Okay. There we go. All right. So next up is our total ionic. I don't know if you guys can hear the rain is pounding down out there. But that's okay. We're inside, we're warm, and we're doing chemistry. What could be better? All right. The upside is you guys don't have to drive through that rain to get back home after class. All right, total ionic equation. So I'm going to break up the sodium acetate because it's soluble ionic compound. 2 sodium plus 2 of our acetate. Both of these were aqueous. Then I'm going to break up our sulfuric acid. Like so. All right, any questions on how I broke up those reactants? All right, now I'm going to do the products. Let me get our solubility table out of the way. All right, so the products, we have sodium sulfate, so I'm going to break that up. But the tricky thing is that the acetic acid is a weak acid, so you cannot break it up. So I'm going to go ahead and write this in one in purple. 2 acetic acids, like so. It is aqueous, that's true, and it does break up a little bit, but not very much. So because it is a weak acid, we need to leave it together. We only break up strong electrolytes, and that is a weak electrolyte. So I know that was a source of confusion for a lot of you. Any questions on how I wrote that out or why we're keeping the acetic acid together? Okay. All right, it looks like we have someone new. Welcome. They're just labeled as iPhone, but welcome, iPhone. All right. So what were the spectator ions that y'all found? Yes, so I'm seeing sodium and sulfate. So sodium and sulfate like so. Any questions on why sodium and sulfate are our spectator ions? All right. Okay, so next up we write down what's left over, and that will be our net ionic. And so here, I'm going to go ahead and bring down the 2C2H3O2 minus plus 2H plus 2 acetic acid like so. All right, but I'm not done with it. What do we need to do? Reduce, yes, excellent. A couple of you caught that. We need to reduce. They're all 2, so I can reduce this to 1, 1, and 1. And I'm actually going to go ahead and do that by just erasing them. So boom, like so. All right, and earlier there was a question of which one of these 2 reactants had to come first. It's fine like this, or for those of you who would prefer, you can bring this to the front and this to the back. So it's up to you which way you want to write those, as long as they're both written as reactants. All right, so questions on anything here for the net ionic? And I see a question, does the net ionic have to be reduced? And the answer is yes. The reason we did not reduce the last one is because there was no way to reduce it. It was a 3, a 1, a 3, and a 1. So we couldn't reduce it. But for this one right here, we originally had 2, oops, get this out of the way, 2 and 2. So you can reduce those 2's to a 1. So in this case, you must. So I'm going to go ahead and write reduce. And then we're going to write H plus our acetate going on to acetic acid like so. And again, this reaction happens because we form a weak acid. So questions on this one here? All right, so these are really tricky ones where you form a weak acid. And when we have a question like this on a test, it is very frequently missed. So I'm going to give you a little warning right now. So be careful. A weak acid does cause the reaction to happen. So if you can form a weak acid or a weak base, this reaction is going to happen. All right, so questions on anything so far? Okay, so I have a little bit more that I want to do with you guys, but why don't we take just like a 5-minute break to stretch? So let's come back about, say, 6:55, just take a little stretch break. And then we'll do about maybe 15 or so more minutes. But I am here during break, so if you want to message me, so if you do want to message me, I'm here. Or if you just want to unmute and talk as well. Looks like we're losing a few people. so let's go ahead and get started again. So any questions on what we were doing with net ionic equations? Okay, so let's go ahead and move on, and we're going to start talking about titration. So this is the lab that we would have been doing tonight, so hopefully it doesn't make you too sad to look at it. So the idea of titration is that we are going to add a amount of what we call a titrant. It's one of your reactants, and we're going to add it very slowly, and in the end our hope is that we have a perfect reaction, which means we have nothing in excess. And that's what titration is used for, to try our best to get those perfect reactions where you don't have any limiting or excess reagent. They're just both mixed exactly right. And we normally use them for acids and bases, but they can be used for other things. In fact, they can be used for any kind of a chemical reaction where we want a perfect reaction. And the reason we want a perfect reaction usually is because we want to use this to figure out what is the molarity of something. How much acid is in that solution, how much base, or how much of something else, how much fluoride is in there, how much chloride. All of those things can be done by titration. So what you see here is in the first image, this one right here, we have an acidic solution in our flask, and in the burette, which is holding the solution up at the top. So this is our burette right here, which I'm not very good at coloring in the lines, but that's your burette. It is traditional for the burette to contain the base, although it doesn't have to. Once the base starts going in, we see a little bit of pink in here, which I actually just colored green. That little bit of pink, and that is from an indicator that we usually use called phenolphthalein. And phenolphthalein will turn pink in basic solution, but it's colorless in acidic solution. So it's really good for titration, so that once we make a basic solution, it turns pink like so. And if we were in the lab right now, I would tell you, you want the faintest amount of pink possible. You want it to just barely be basic, but those of you who took our Chem 2 class, you know how hard that is. You know how easy it is to just put a drop too much, and then it goes bright, shocking pink, which means you overshot your endpoint just a little bit. You put just a little too much in there. So the upside is you get to do this all with calculation, and you don't have to look at that shocking pink and be like, oh my gosh, it's way too pink. So that's the upside. The downside is you don't get to play with our burettes and get that beautiful slight pink color. All right. So our indicator is a type of dye, and again, it changes color based on the acidity of the solution. So phenolphthalein, which we use for titrations of acids and bases, works really well because it's colorless when it's acidic, and it is pink when it's basic, but it's not the only indicator. We have all sorts of different indicators, and they change at different pHs. Some will change colors at pH 3, pH 5, pH 7, all sorts of different ones. And then there are two very important vocabulary words that I want you to know. And those are endpoint and equivalence point. They are very similar, but they're not identical. So the equivalence point, that is theoretical. That's what you calculate. That's what we're about to calculate. That is when you have equivalent amounts of acids and bases added. But the endpoint is experimental. So it is experimental. It is the first appearance of color change. It is that you are adding this base drop by drop by drop, and your partner suddenly screams out, "Stop, I see pink." It is where you see that pink. Now, everybody's eyes are a little different, and because of that, everybody's going to get a slightly different endpoint. So the endpoint is experimental. It's not exact, not unless you had perfect eyeballs and you were in a perfect lab and you were a perfect human, and you are a perfect human, but you may not have perfect eyes, and we definitely don't have a perfect lab. All right, so that is why the endpoint is different than the equivalence point. So the equivalence point is calculated. So just like our theoretical yield, we calculate it. It is what should happen. Experimental, that is the actual. That is in the lab. So your endpoint depends on how good you are as a chemist, how good your eyesight is, all this great stuff. Oh, and I hear someone did this once and the dropper fell off and all the base fell into the solution. Wow, that must be shocking bright pink. That's very sad. Every once in a while that happens. Okay. So other questions or comments or war stories about titration? Titration can be fun. It can be painful as well. I mentioned to you that we do have a lab tech and we have student lab techs as well. And one of the things they do is they find the molarity of the solutions that they give us. So they do have to titrate them to find the molarity before they give those to us. All right, so here's our first titration problem. It says we have 19.4 milliliters of sulfuric acid and it's being used to neutralize 29.5 milliliters of a 1.790 molar NaOH. We're going to find the concentration of the acid and molarity. So now the word neutralize, that is just what we call it when we have an acid-base reaction. So they're neutralizing each other. So first off, I'm going to write up the chemical reaction. So we have our sulfuric acid plus our NaOH. This is a double replacement. So I'm going to write out my ions, H plus, SO4 2 minus, sodium and hydroxide like so. All right, any questions on how I wrote out those ions? Okay, so from here we combine our outer ions and our inner ions. So what are our products? Anyone bravely want to venture a guess about what our products are? Excellent. So I'm seeing Na2SO4 and I am seeing H2O like so. All right, any questions on how we got those products? All right, anyone want to bravely venture some guesses on how we're going to balance? Any thoughts on the balancing? Or are we already balanced? All right, so I'm seeing a 2 by the NaOH. Excellent. All right. Anything else we need in here to balance? Excellent. 2 waters. All right, we got some fast balancers in here. All right, any questions on anything here on how we came up with our chemical reaction or how we balanced? All right. So now what I'm going to do is take our chemical equation and I'm going to copy it down here. There we go. All right, so remember you guys can mute yourself. I hear someone guzzling what I'm going to assume to be water, so feel free to mute yourself unless you want to guzzle for the audience. All right. Okay, so we said we have 19.4 milliliters of sulfuric acid. All right, and then for our NaOH, it looks like we have 29.5 milliliters. And then we have 1.790 molar for the NaOH. All right, so this problem is shockingly like something we called solution stoichiometry before. And we talked about which number we were going to start with. And what I told you is that I recommend that you start with the chemical you know more about. Oops. All right, trying to draw a perfect box. Try one last time. There we go. All right, so we start with a chemical that we know more about. And does anybody remember if we start with molarity or if we start with volume? All right, so I'm hearing votes for volume and I'm hearing votes for molarity. Anybody else want to venture a guess? All right. So it's about tied 50-50 right now. So what I'm going to tell you is we're going to start with volume. What we said before is that molarity is a conversion factor, and we don't want to start with a conversion factor. We always want to start with a number that's not a conversion factor, and that's why we start with our volume. Okay. So any questions on why we're going to start with the volume of NaOH, the 29.5 milliliters? All right, so I'm going to start with that 29.5 milliliters, and we're going between two different chemicals here. So I'm going to make sure to always label which one I'm talking about. And this is the NaOH. So I'd like to use the molarity as a conversion factor, but molarity is moles per liter, so I've got to get into liters. So I'm going to say there's 1,000 milliliters for every 1 liter like so. Now I can put in the molarity as a conversion factor. So it's this molarity right here that I want to use. And I'm going to say for every 1 liter, there's 1.790 moles. And these are moles of NaOH. All right, so any questions on how I took, oops, sorry for the background noise there. Any questions on how I took the molarity and I split it up to make it that conversion factor of moles per liter? Or any questions on what we've done so far? Am I hearing a question from someone or just some background noise? Maybe just some background noise. Okay, so right now we have moles of NaOH. Let me actually move to the next one here. But we really want moles of sulfuric acid. So let's start with the moles of NaOH. What number am I going to put in front of moles of NaOH? Excellent. And let me answer a question here. All right, so I did get the question of whether or not you had to show the milliliters to liters, and the answer is no. If you want to start with it in liters, you're more than welcome to. All right, so we said 2 moles of NaOH, and how many moles of sulfuric acid? Excellent. 1 mole of sulfuric acid. All right, so any questions on how we've set this up so far? So this is our dimensional analysis. And go ahead. So milliliters cancels with milliliters. Liters will cancel with liters. Moles of NaOH with moles of NaOH. And we're going to be left with moles of sulfuric acid. So let's go ahead and calculate this one together. 29.5 times 1.790. And in the bottom, I have 1,000, and I have 2. All right, for those of you calculating at home, did you get something similar to this, 0.0264? Excellent. All right, so this is in moles of our sulfuric acid. All right, but that's not what our problem asked for. It asked for the molarity. So molarity is moles per liter. So I'm going to say 0.0264 moles of our H2SO4. then what volume do we use? Are we going to use the 19.4 or the 29.5? Excellent. So I'm seeing the 19.4. Yes. So that's important. If you're finding the molarity of sulfuric acid, you must use the volume of sulfuric acid. All right. But how do we write 19.4 milliliters in liters? Ah, yes, and I see and convert from Tasso. Anyone want to brave what is that in liters? Yes, excellent. 0.0194 liters of H2SO4 like so. All right, any questions on what we've done so far here? Okay, go ahead and take a moment and calculate out that molarity for H2SO4. Once you get your molarity, go ahead and type it into our group chat. All right, excellent. Looks like everybody's getting similar numbers there. Looks like 1.36 molars, which just about everybody's getting. Anyone get something different? Okay. All right, so this is our molarity. So for these titration problems, my recommendation is that you do it in this two-step process where the first step is your dimensional analysis. So you don't have to show me the milliliters to liter step, but I do need to see you using the molarity as a conversion factor, and I need to see you using that mole ratio. Then my recommendation is that you do in a second step your molarity, moles over liters, to get that final molarity. So any questions on what we did here with our titration problem? Okay, so I'm going to tell you titration problems, and I know it sounds like I say this about everything, but titration problems are really important, and there is a very high likelihood you will see this on your next exam. We'll get more practice on this, and of course you're going to get some practice on it on your homework. But any questions on the titration problems? Any questions about those net ionic equations or that homework example that we went over? You guys are like, nope, let's go. Okay. So I will be here on this same web station until 9:45. So you're welcome to stay for office hours, or you can leave, and then between now and 9:45, if you feel like you had a question, you want to come back and ask me, you're welcome to. But this is going to be the end of our lecture for today. But let me ask you all a question. So does this seem like a format that will work? I know it's not as nice as being in class, but will this work out? Oh, excellent. So it sounds like it is working for most of you. Oh, it works fine. Okay, yep, excellent. Oh, excellent. So if there's anything about this that just isn't working for you, maybe, I don't know, anything about it, please let me know. You're welcome to email me. You're welcome to group chat me or stay on afterwards. Just let me go right back to our upcoming due dates. So I did, for those of you who weren't here at the beginning of class, I added a note here, and that is with all of the craziness going on out in the world, the due dates are going to be recommended due dates. If you need some extra time, just let me know, but be careful about putting things off because things do start piling up. But if you need more time, just let me know. So my hope is that I will get Chapter 4, Part 1 before 10 p.m. tonight, and the Lab 3 before 10 p.m. tonight. But again, if you need more time, then you can just let me know that you need more time on those. And for Wednesday, I will post a new URL, so it'll be a new web address different from the one that you used today. All right, questions on anything for me? I know you said about lab being fun. So, okay, good question. So we got a question about labs. So our plan was to record the labs and give you data. Unfortunately, the schools just decided that they don't want anybody on campus. So that at this point is not going to happen, not until they start allowing people back on campus. So it is effectively closed now. So no students, no staff, except for emergency personnel on campus. So we're just waiting to hear from the school for when we can get back on campus to record those labs. Whoops, and my cat suddenly wants to say hello. Aw. Okay, you can go. She wanted to say a brief hello. It's just a drive-by. All right, so questions on anything else? All right, so I will be here till 9:45. Feel free to stay or to join me back, leave and join again later between now and 9:45. So for those of you leaving, bye. It was nice to see you. Thank you all for coming. Aw, thank you. All right. Aw, thank you. She is my sweet little kitty. Aw. Thank you all for coming. You're very sweet. Aw, thank you. My cat will always has a nice evening.